Okay, so as I said that we are going to start with the concepts of integration today. So let's begin by understanding the definition of integration as an operation. This is session number 10 or session number 9. Session number 9 for us, yes. Okay, so as I said, we will start with the second part of calculus today, which is integral calculus. So integration, it is again an operation that is conducted on a function. With respect to its variable. So there are two types of integration, or two types of operations in integration. The first is called indefinite integration. So by definition, what this operation does is indefinite integration operates on a function to give its what is called its antiderivative. So you'll understand what antiderivative means. So basically the operation results in the inverse process of differentiation. Because differentiation gives us derivative. This gives us antiderivative. So let's understand what the meaning of this definition is. So first of all, the symbol for indefinite integration, this is called the integral symbol. Okay. So integration is applied to a function with respect to its variable. Okay. So this is indefinite integration. Of fx and with respect to the variable x. So for example, if I write integration h dt, so this will be read as indefinite integration of h with respect to t. So the understood meaning here is t is the variable and h must be a function of t. So just write down this part first. This is just about the symbol. Then we'll discuss the definition and meaning of integration further. So this is just the terminology of the operation. Okay, so let's now understand the meaning of the term antiderivative and what indefinite integration does. So the operation of indefinite integration on a function, the output of that is another function which is called the antiderivative. Okay. So Ix is the antiderivative of fx, which implies that if we differentiate Ix, we will get fx. Okay. So this is the meaning of the term antiderivative. Antiderivative of a function fx is such a function Ix whose derivative gives us fx. So integration of fx is equal to Ix means differentiation of Ix is equal to fx.
So can you repeat? So
Yes.
can you repeat this?
Yeah, just write down the definition, better. Antiderivative, then we'll understand with examples. Okay. So integration of fx gives us another function Ix. Ix is called the antiderivative of fx. So the meaning of that is if we differentiate Ix, we'll get fx. Just the same thing that I've written down over here. Okay. Yes.
Okay.
Sir, if you're integrating f of x, then why have you written dx also?
Sorry, come again.
Sir, if we are integrating d f of x, then why have you written dx?
Because that indicates it's with respect to what variable. Okay. So that is very important in the symbol of integration, as I've explained over here. whenever we integrate a function, we have to write the integration symbol, the function, and d of some variable. So which is the variable we are integrating with respect to, in this case, x. So we have to write dx over here. Understood now?
Yes, sir.
This is part of the terminology. Like the operation of differentiation, it has dx in the denominator because it shows that we are differentiating with respect to x. Like that, the operation of integration will have integration symbol, a function, followed by the symbol dx. So the dx will show us that we are integrating with respect to the variable x. Okay, so what this also means, in other words, is that ix, which is the antiderivative of fx, this means that fx is the derivative of ix. So basically, we are talking about two functions which are related in such a way that this is integration, indefinite integration, of course. Okay. This is differentiation. That is how the two are linked to each other. Okay. So now, for example, we'll take very basic thing that differentiation of x square is equal to 2x. Okay. But also differentiation of x square plus any constant is equal to 2x, where c is any constant. Okay. So integration of 2x in general will become x square plus c. So you can see the relationship between this function x square plus any constant and this function. So between the function x square plus c and the function 2x, this relationship is such that okay, integration of this gives us this, which means that if I have this function to begin with, then differentiation gives us this operation. So in general, we can say that 2x is the antiderivative. Sorry, 2x is the derivative of x square plus c. So that means that x square plus c is the antiderivative of 2x. So integration gives us the antiderivative. This is the meaning of the operation. So hope with this example, it is more clear now what we mean by the term antiderivative. Yes, Srija. Srijata, you have a question, beta?
Yes, sir. Sir, in the above example, why have you written indefinite integration?
Srijata, can you speak a little louder into your mic, please? Can't hear you.
Sir, in the above example, why have you
Yeah,
specified indefinite integration?
yeah. Why have we specified? Okay, because there's another type of operation called definite integration, which has a different meaning, beta. Okay.
Yes, sir.
So this operation that gives us antiderivative, this operation's name is only called indefinite integration. Okay, na?
Yes, sir.
Okay, now as you can see from this example, the antiderivative of a function will always have a constant term which could take any value. So that means the antiderivative of a function is a family of functions. Actually, it's not exactly a unique function. So that's another reason why this operation is called indefinite, because it gives us an indefinite output. Okay. So the antiderivative of a function ix, it is actually not exactly a function ix, which is antiderivative of fx. So we can't really say that it's a specific function. Ix is actually a family of functions. Okay. Because Ix includes a constant term such that this constant can be any real number. Okay. So that's the example we are just talking about, that if we integrate 2x dx, we will get in general x square plus c. So x square plus c is the antiderivative of 2x. Now 2x, as you can see, it is a specific function. Fx. But x square plus c is not a specific function. It is a family of functions. So for example, it could be x square, it could be x square plus 1, it could be x square minus 1, it could be x square plus 10 raised by 3, it could be x square minus 10 raised by 6, and so on and so forth. So this is a family of functions given by the general symbol x square plus c, where c is a constant term, which could be any real number. Okay. So that is why, that's another logic of, you ask the question why we call this operation indefinite integration. So that is the logic of calling it indefinite integration. Okay. So therefore, this operation is called, because it does not give us a definite answer, it gives us an indefinite answer. Okay. Another example you can see is, suppose we integrate cos x with respect to x, it will be sin x plus c. Okay. Because we know that differentiation of sin x plus c will be differentiation of sin x plus differentiation of c, which by definition will be cos x. So we can say that sin x plus c is the antiderivative for cos x. So this is a definite function cos x, but this is an indefinite answer. So this is a family of functions. It could be sin x plus any value, as long as that value is a constant and not a variable. Okay. So another thing here, that c is called the constant of integration. It's called the constant of integration. Okay. So if I say what is the integration of cos x, then sin x is the wrong answer. It is sin x plus c. Or if I ask you what is the antiderivative of cos x, the correct answer is not sin x. It is sin x plus c. Because as you can understand, sin x is not the only function whose derivative is cos x. Sin x plus any other constant term will also give you a derivative of cos x. So that means antiderivative of cos x is the general family of functions sin x plus c, where c is any constant term. So this you can say is the logic of why it is called indefinite integration. And okay, of course, there is another operation also called definite integration, and we'll come to that. Okay. So another reason for calling it indefinite is that we have to understand there are two different types of operations. One that gives us a definite answer, one that gives us an indefinite answer. But we should always think of this operation as something that gives us antiderivative. So if the question is, I have a function fx whose derivative is fx, then the answer is that we integrate fx, calculate the antiderivative. So that antiderivative's derivative is fx. Ix's derivative is fx. Okay. So now let us look at some basic formulae of integration. So we are still talking about indefinite integration. So now the most basic one for algebraic functions is that integration of x to the power n is x to the power n plus 1 divided by n plus 1 plus the constant c for all values of n which are real, sorry, all real values of n other than minus 1. Okay. Or you can say that it is for n not equal to minus 1. All values of n other than n equal to minus 1. Okay. Now the logic of this operation is very simple, that since differentiation of x to the power n is nx to the power n minus 1. Okay. So therefore differentiation of x to the power n plus 1 is equal to n plus 1 x to the power n. So that means differentiation of x to the power n plus 1 divided by n plus 1 is x to the power n. So that means differentiation of, so I mean there is no separate proof needed for this, okay, because this just comes from this actually. This formula, this fundamental formula of differentiation is actually the reason why we have this fundamental formula. Okay. Or in general, we can generalize this by taking a constant also inside, because you know that derivative of a constant is 0. Okay. So along with this fact, if we also use the property of differentiation, that differentiation of a constant is 0. So we get this, that differentiation of any term like this is equal to x to the power n. So that implies that integration of x to the power n should be, so integration with the symbol dx. If we don't write the symbol dx here, actually the operation doesn't make sense. So we have to write the symbol dx after the function in the integration operation. So this is the logic of this formula. But more importantly, anytime we have a term which is a power of x other than power minus 1. Now we'll discuss what happens when power is minus 1 also. But as you can see, this operation cannot be applied to the term n equal to minus 1, because it will give us a this thing undefined value. The denominator here n plus 1 on the right hand side will become 0 if I take n equal to minus 1. So we cannot use this formula or this definition for the value n equal to minus 1. It is valid for all values of n other than minus 1. So another way of saying it is that this is for any n other than n equal to minus 1. So by now you have done so much of differentiation that you will see that this will not be really a challenge for you. You are already familiar with how to apply formulae like this, like an algorithm. Okay. So for example, if I give you integration of x square, you'll be able to figure out very easily that this is x cubed by 3 plus c. And you can also check that differentiation of x cubed by 3 plus c will give you x squared. Okay. Similarly, if I give you an example, integration of square root of x with respect to x, you can understand this is x to the power half. So applying this formula, so that will give us 2 by 3 x to the power 3 by 2 plus c. So now you can check here that differentiation of 2 by 3 x to the power 3 by 2 should give us root x. So it's basically a very simple thing. It's the reverse operation of differentiation. Okay. But because differentiation of a constant is 0, this reverse operation does not result in a specifically defined integrand, specifically defined antiderivative, but more like a general family of functions which has that constant term which is indefinite.
So I still don't get what's the use of writing dx next to x root x.
Okay, it's more like a convention beta. What is the use of, like, for example, if we want to differentiate a function with respect to x, now we have to, this symbol is for differentiation, okay, with respect to x. So what is the dx in the denominator actually signify? That we are differentiating with respect to x now. Like that, this
Okay,
symbol,
sir.
understood, no? So the person who's reading the symbol should understand that what is the variable of with respect to which we are integrating. So the dx signifies that.
Okay, sir.
Now, sometimes in everyday language, we use the term integration for this operation also. But we should understand that this operation is technically called indefinite integration, because there is also another operation called definite integration. We will come to that also. Okay, so let's look at another quick example. So let us say the derivative of a certain function fx is equal to 1 by root x. Okay, and its value at x equal to 0 is equal to 2. Find fx. Okay, very good. So as you can see that derivative of a function equals to 1 by root x. Okay. And the function's value at 0 is equal to 2. Okay. So that means if we compare this function and if we compare 1 by root x, this is differentiation. So that means this should be integration. So the fact that differentiation of a function is 1 by root x given to us in the question, it implies that integration of 1 by root x should give us the function. So here, this is basically playing the role of antiderivative. This is the antiderivative for 1 by root x. So now we'll just use the formula of integration. X to the power minus half. So x to the power minus half plus 1 upon minus half plus 1. So this shows us that this is 2 root x plus c to begin with. Okay. Now what is the value of c? For that we have the second piece of information, that not f prime, but oh sorry, it is f prime. So this is given to us as 2. So we'll use this. So it means that the particular function which has both these properties, that its derivative is 1 by root x and its value at 0 is equal to 2. So that particular function is this one. So you can see that you can check that this function satisfies both the given conditions. First given condition was that derivative of that function should be 1 by root x. So that is also satisfied by it. And second given condition was that the value of the function at 0 should be 2. So that is also satisfied. So this is the simple meaning of doing this operation, that it should give us a function which satisfies this given condition. Okay, so now we come to the exception for the x to the power n formula. Okay. For the formula integration of x to the power n dx, okay, for all n except n equal to minus 1. Now what about integration of this? This becomes ln x plus c. Okay, because we know that differentiation of ln x is 1 by x. So integration of 1 by x is ln x plus c. So this is the exception to the above rule. Okay. Now let's look at a couple of properties of integration before we come back to more formulae. So integration of a constant, or let's write the constant with a different symbol. So that's one property. Then another property is integration of a constant times a function is the constant times integration of that function. And the third property, as you might have guessed, is like the distributive property for integration. Which applies to both sum and difference. So you can see it's like follows a similar pattern to differentiation. Okay, so just work out these 4 simple examples as a bit of practice, then we'll move on to more formulae.
Sir, but what is integration exactly? Sir, on a slope, what I'm trying to do is I'm trying to find every smallest point and then I'm adding them together.
Sorry, come again, beta.
Sir, when we differentiate, what we're actually doing is, right, on the slope, we're trying to find the value of every minimum, every smallest point, but in a generalized form. In integration, am I trying to add all of them?
No, in differentiation, we are trying to find the slope of the tangent at a particular point. So integration is the reverse. If the slope of the tangent at a point is this value fx, okay, then what is the value of the function at that point? That is your ix. You understand? It's the reverse process of differentiation.
So just
Differentiation gives us the derivative. Derivative क्या होता है? It is slope of the tangent.
at a point. And now
Yeah.
we're asking to find a point from the slope.
Yeah.
Okay, sir.
Sir, so when we're doing addition, do we get two C's separately?
Sorry, do we get?
When we do addition of two terms, then we'll get two C's, right?
Yeah, very good question. We'll get two indefinite constants, but we can combine them and write a single value. You know? Like separately when we integrate, so we'll get two constants, let's say C1 and C2. So we can add them and write them as a single constant C, you know, because C1 and C2 can individually take any real values. No? So there's sum can also take any real value.
Yes, sir.
Okay, so we write them finally in the equation. In the final antiderivative term, we combine them and write them as a single constant C.
Okay, sir.
Okay. Yeah, so let's look at the answers of this. So many of you have sent me the answers, they are correct, okay, mostly. So the first one, we have to just convert it to a single power. So this is x to the power minus 3 by 2. So its integration will become n plus 1 upon n plus 1 plus c. So as you can see, it will become minus 2 x to the power minus half plus c. We can also write it as minus 2 by root x plus c. So this is the integration of this. Similarly, the second one, you can first separate it out as this. You can bring this constant out. This is the step I was talking about. We can write two individual constants here. Okay. Or we can combine this two constants and write it as C, because C1 and C2 can individually take any real values. So their combination C1 plus 2C2 can also take any real number value. So we'll just combine them and write them as a single constant term. So antiderivative of this function is this. Okay, so similarly, the third one, see that separate it out like this. Write a combined constant for the two integrations. Now you can always check your answer yourself by doing the differentiation test, that finally whatever answer you get as the antiderivative, If you differentiate it, you should get the original function which you were integrating. So in that sense, you can self-check each of your solutions. Okay, so people hope these questions are clear. Now moving on to some more fundamental formulae for indefinite integration. So we have integration of sin x is equal to minus cos x plus c. The reason for this is very simple, that differentiation of cos x is minus sin x. So then integration of cos x is sin x plus c. Integration of tan x is natural log of sec x plus. Now this one is a little more complicated in proof. Okay, so do the proofs of these as homework today. Use this kind of chain rule method to differentiate the antiderivatives and prove that they are the values as per the formula. Okay, so now we move on to the next level of integration, okay, which is integration by substitution. Okay. Now, this in itself is a very wide and complicated subject in mathematics, but over here for our physics purpose, we will look at some, you know, like basic formats of integration by substitution. So the first type of substitution, or the first format, is when we are substituting of a linear term. Okay, so our integration is of this type. We are integrating this type of a function where ax plus b is a linear term. Okay, so a and b are constants. For example, suppose we are integrating square root of 2x plus 1 with respect to x. So we can see that the function is square root of x, but here we are taking where a is equal to 2 and b is equal to 1. So this type of integration. So let's see how we do this. So in this we do a direct substitution. Ax plus b is substituted as z. So therefore dz by dx is equal to a. Therefore dx is equal to dz by a. So the integration, which was in this, we substitute this term and we substitute this term. So the integration becomes This becomes like a direct formula for the integration, where Ix is the antiderivative of fx. Constant of integration is included in Ix. Okay. So just note this down as a method. We will do some examples and this will become very clear to you how exactly it is done. So this is the most basic type of substitution that comes under the category or comes under the subject of integration by substitution. Now there are many different types of substitutions, and only few of them we will study in physics over here in basic calculus. Many more of them we will study in advanced calculus and maths later. It's a very fascinating subject actually, integration by substitution. Okay. It's a bit manipulative also. So it can be considered as one of the more difficult things in calculus. Okay. But here the level of substitution that we learn for our physics applications are going to be very simple substitutions like this linear term one. Okay. So nothing to worry about at our level here. Okay, so let us see a simple example of this kind of substitution. So what we can do now, eventually we can use this as a direct formula. Okay, eventually we can use this one as a direct formula, that anytime we have integration of any term like this, that just becomes this. Okay, where basically Ix is the antiderivative of fx. Okay. But you should also understand the logic of this formula. The logic of this formula comes from substitution. Okay, so this basically comes from the substitution steps which we have seen above. So let's understand a couple of examples with the substitution steps first. Okay. So let's pick up that question that we were discussing about earlier. Square root of any linear function, let's say 2x plus 3 or 2x plus 1 or whatever. So if I'm okay, so I know that, so basically formula wise what I'll say is that I know that integration of square root of x is equal to 2 by 3 x to the power 3 by 2 plus c. So therefore integration of square root of ax plus b should be equal to 1 upon a into 2 by 3 ax plus b to the power 3 by 2 plus c. So in this case, integration of 2x plus 3 should become 1 by 3 and you will see that by using this formula, this antiderivative that we have got, it will check how to give you the correct value. You can check that differentiation of this term will give you this term. But let me do that step by step over here. Okay, so this is direct formula. So this is giving me by direct formula.
2 by 3, sir.
Sorry.
So 2 by 3, right? Sir, if I differentiate
Which one?
this
2 by 3 y. It is, see, power is half now. So n
Yes,
plus
sir.
1 now. You understanding? X to the power n plus 1 upon n plus 1. No? So it's 2 by 3 x to the power 3 by 2. Got it now?
No, sir. Sir, here in this one, it should be. Sir, how did you get 1 by 3? I don't understand.
Because there is this 1 by a term ना बेटा. तो यहाँ पे a क्या है? 2 है ना? A is equal to 2 ना बेटा?
Yes, sir.
Understood? So it's 1 by 2 into 2 by 3 into 2 by 3
Achha,
into 2.
okay, sir. Yes, sir.
Okay. So anyway, I'm doing this step by step also. So this is the direct formula method. Now let's do this step by step. Okay. By steps, how we'll do. So the first step is we will substitute. Okay. So we will substitute 2x plus 3 as z. So this is like a dummy variable for us. Okay. So now the moment that happens, so we can see that dz by dx is this. So it is 2. So we can see that dx can be substituted as dz divided by 2. So this is one thing we will substitute. Okay. And this is the other thing we will substitute in the integral. So our integration, the original integration, which was integration of 2x plus 3 with respect to x, that will become integration of z with respect to dz, but that dx will be substituted as dz by 2. So this will become 1 by 2 z to the power half dz. So the next step now is we execute the integration. So So 1 by 2 into z to the power half plus 1 upon half plus 1. Okay. Plus whatever constant of integration. So 1 by 2 into 2 by 3 is z to the power 3 by 2 plus c. Okay. So that becomes z to the power 3 by 2 divided by 3 plus c. Now we have to do the resubstitution. So we have to resubstitute our dummy variable z as 2x plus 3. So that will give us the final step, that integration of square root of 2x plus 3 with respect to x will give us 2x plus 3 to the power 3 by 2 divided by 3 plus c. So you can see that what I've done by direct formula here, this one is basically going by all the steps over here. So one critical, yeah.
Sorry, sir. Once we start solving, do we need to do this long method, or we can just put the formula directly?
A little bit louder, please, but I couldn't hear you.
Once we start solving the sums, do we need to use this will we ever need to use this long method, or can we just?
No, we don't need to apply the steps. Okay, the steps is just for your understanding. So basically, you know, any integration we have of this type now, that integration of some function of a linear term, okay, we can just directly apply this formula. It will be antiderivative of that function applied to that linear term, but divided by the coefficient of x plus c, where we understand that I is such a function that it is antiderivative of this original function. Got it understood? So basically our method, our go-to method at the exam level will be this, that I had this function given to me, so I'll directly apply the formula. Okay. This is the direct method. Okay. And this here is the explanation of that method. So for this first type of substitution, substitution of a linear term, we don't need to do the steps at the exam level. Once we are comfortable with the idea of it, we can directly use the formula.
One more thing, sir.
Sorry, come again, Beta.
One more thing. So when we were doing, if we just, without using this formula, if we don't have a root, suppose just a simple linear equation, can't we take it as integration of two different terms, and then will we get the same answer?
Yes, you will get the same answer. Okay. So for example, if you were just doing this, if you were just doing, let's say, integration of 2x plus 3. Okay. So that will be two ways of doing this. One is you separate it out. Okay. So you get x square plus 3x plus c. The other is you can write it as z dz divided by 2. Okay. So that will be z square by 2 plus c. So that will be 2x plus 3 square by 2 plus c. So you will see that you will get x square plus 3x. Okay. Plus you will get another term 9 by 2 plus c. But 9 by 2 plus c itself is a constant term. Okay, so it's the same as this. So this is ultimately the same as this. But you can say that this is unnecessary. Here, doing this method is unnecessary. You don't need to do this method. Okay, both methods are correct, but this is unnecessary. Okay. Whereas, like in this function which I've given, square root of 2x plus 3, it's compulsory to use this method, because we cannot directly integrate square root of 2x plus 3. Got it, no? Similarly, if I had 2x plus 3 whole square, for example, you could go by either of the methods. You can substitute 2x plus 3 as z and use the z square integration formula, or you can actually expand the 2x plus 3 whole square using a plus b whole square and use the sum property. So both the methods become feasible over there. But again, probably there the substitution method will be faster.
Yes, sir.
Okay. So now this applies not only to like algebraic functions like the ones we are talking about right now, but this also applies to trigonometric or exponential terms. So if I have, for example, e raised power some linear term or sine of some linear term, then again we have to use this formula. So just make sure you're clear with this first, then we'll do some more examples. Yeah, Dhruv, I'll scroll up. This is the part you wanted to write down, Dhruv?
Yes, sir. Sir,
Okay.
just give me a minute. I'll note it
Yeah.
down.
So what if I was to differentiate the same question, sir, in terms of 2x plus 3, integrate.
Sorry, come again.
So if I integrate root 2x plus 3 in terms of 2x plus 3.
So that is that you're taking 2x plus 3 as a variable z, no?
Yes,
So
sir.
you're integrating root z with respect to z. So that is 2 by 3 z to the power 3 by 2, no?
Okay, sir.
You understanding, no?
Yes, sir.
Okay, so Dhruv, this is clear, no? No?
Yes, sir.
Okay. So now, for example, if I have integration of sine 2x, this will directly become what? It will become minus cos 2x by 2 plus c. Because you can see here that this is where f is the sine function and ax plus b is 2x. So a is equal to t, 2b is equal to 0. Or if we have integration of e raised power 5x plus 3, let's say, then directly it is e raised power 5x plus 3 divided by 5 plus c. Because here the function is the exponential function. and the linear term is 5x plus 3. So any integration like this we can do directly now. These are all examples of this.
Sir,
Yes.
won't that be 2x squared by 2?
Sorry, come again, Rita. If
The sine 2x integration.
Achha, if it's a non-linear term, saying like that.
No, I'm saying the answer, won't it be minus cos 2x squared by 2?
No, why it be because see the integration of sine x, na, that is minus cos x, na? Got it, na? So the integration of sine of ax plus b will be minus cos of ax plus b divided by a plus c. So, no, because you would have substituted ax plus b as z, na?
Yes, sir.
So dx is becoming dz by a. So the integration is becoming integration of sine z dz, but divided by a. So 1 by a comes outside. Okay. So next step, this becomes this. Okay, so once you are clear with doing this kind of substitution, now we will come back to more complicated substitutions also. But before that, we will look at the second type of operation in integration, and that is called definite integration. So definite integration does not give us antiderivative; it gives us a definite value. Okay. So definite integration, the operation, okay, applied to a given function results in a definite value. Okay. So definite integration symbol is like this, or sometimes it is just like this. Okay. So this symbol is read as definite integration of the function fx, okay, with respect to the variable x, okay, from lower limit x equal to a to upper limit x equal to b. Okay. So these symbols here, they are called the limits of integration. So always the one written in the lower part of the integration symbol, it is called the lower limit, and the one written on the upper part of the integration symbol, it is called the upper limit. Now we'll see that this has significance in terms of geometrical meaning also. But first, let us understand the terminology, then the definition, and then we will come to the interpretation geometrically. Okay. So this is just a symbol.
Sir, is there any chain rule like method we can use for this? Like for example, so for the previous topic I'm talking about the previous topic. Excuse me, sir.
Yeah, Janvi, you have a question, beta?
Yes, sir. Sir, is there any chain rule like method we can use for this for so for the previous topic? So for example, I'll differentiate the function according to a simpler form of it, which integrate, which I will again integrate according to dx only.
You will see that substitution is actually the equivalent of chain rule for integration only. Okay. Only so far we have seen this simple type of substitution where it's only a linear function. Are you understanding my point, beta?
Yes, sir.
Suppose instead of square root of 2x plus 1, we had square root of ln x or square root of e raised power x or square root of sin x, then we would have a more complicated substitution for doing. Okay. But there is no systematic method like the chain rule method that we have for differentiation. Okay. Because differentiation is a fundamental operation of calculation of rate of change. But integration is like a derived operation, which is like the reverse process of differentiation.
Yes, sir.
So there are like certain tricks that we use for substitution of more complicated functions, and we'll discuss those tricks. Like as I told you, that integration by substitution is a very wide and fascinating topic in mathematics, but only some of the types of substitution we'll be studying here, in which like first of all, because we will need only some of them for our physics application, and secondly, so that the manipulation part is not too difficult for us. Okay.
Yes, sir.
Okay. But first I want to introduce us to definite integration also properly, so that we can get started with doing questions involving integration. Then we'll come back to some more substitution. Okay. Now how this operation itself is conducted, let's understand. So the operation or method of solving this is given by the value of the indefinite function at b minus the value of the indefinite function at p. Okay. Where ix is basically the antiderivative of fx. So let me illustrate this with an example for it to become clear. So for example, if I'm integrating x square from x equal to 1 to x equal to 2, let's say. So I know that the indefinite integration of x square is what it is, x cubed by 3 plus c. So it will become the value of x cubed by 3 plus c at 2. Okay. So it will become 2 cubed by 3 plus c minus the value of the indefinite function at 1. Okay. So ultimately we'll see this will become 8 by 3 minus 1 by 3. So it becomes 7 by 3. Okay, so we get a definite value, as you can see. The indefinite constant cancels out. Okay. So basically over here, this is the value of the antiderivative at the point x equal to b. Okay. Upper limit. And this one is the value of at lower limit.
Sir, what exactly is this value on the graph?
Sorry, come again, beta.
This value, what is it on the graph?
It gives us the area under the curve actually, from A to B. We'll come to that, beta. Don't worry. I'll explain that to you.
Okay.
Okay, so let's first practice this out with some examples. Okay, so let's work out these four values. Okay, then I'll explain to you the meaning of indefinite integration also. Sorry, the meaning of definite integration in terms of graphical interpretation. So just try out these questions and send me the answers, please, all of them.
The next one is not definite.
Anirudh, check your second one's answer once.
Yes.
First and third are correct. Okay.
So the last one is definite or not indefinite.
Last one is,
So definite or indefinite.
the interesting thing is it is definite, okay, because the function is e raised power minus x. Yeah, Janvi, your answers are correct, beta. Aparna, fourth one you have to check. First three are correct. Very good. Fourth one, you just probably just mixed up the sign a little bit. Otherwise, it's correct. Abhinav, correct. Very good. Okay, so those who have worked out the first three, I'm just giving you a hint for the fourth one. The hint for the fourth one is that if you do the indefinite integration of this, it is e raised power minus x with a minus sign plus. Now, because integration of e raised power ax plus b is e raised power ax plus b divided by a plus c. So in this case, your a is basically equal to -1 and b is equal to 0. So you get this. Okay. So this is the hint for this question. Try it out with this hint, you will get the answer. Okay. Now systematically, let's do each of these. So we know that integration of sin x, indefinite integration, is minus cos x. Okay. So this will become minus cos pi by 2 upper limit. Okay. And while writing the limits, you can just leave out the constant of integration. Minus of minus cos 0. So it is 0 minus of minus 1. So that's why it becomes 1.
So is it 0 degrees?
Sorry, beta.
Is that 0 degrees?
Isn't? Couldn't understand you, beta. What was the question?
You said cos 0 is 1, minus cos 0 is 1. So is that 0 degrees?
No, no. Cos 0 is 1, na, beta. So it is minus of minus 1. Understanding now? The value of this function at x equal to 0. What is the value of the function? It is minus cos 0. No? So it's minus 1. No? So it's upper limit minus lower limit. No? Is it clear now?
No, sir.
What is the problem, beta? Tell me which part is the problem.
I'm just not getting how you got cos 0 as 1.
अच्छा, how I got cos 0 as 1? वो तो value होता है बेटा. Cos function. Cos x is basically what? Cos theta is base upon hypotenuse. Na? So if your theta is 0, your basis value is equal to hypotenuse. Na? So cos 0 is 1. Cos 0 is the same thing as
Okay,
sin 90. And cos 90 is the same thing as sin 0, which is 0. Right?
okay, sir.
Okay. All right, let's come to the second one. So now we know integration of x dx is x square by 2 plus c. So this will become 1 square by 2 minus of minus 1 square by 2. So that will be 0. Whereas the third one is using the same integration, okay, but with different limits. Is equal to 2. Yes, Nidhi is very good. That's correct. Saina, correct. Okay, so especially those who have got all three correct for the first three, try out the fourth one now using the hint that I've given. I'll just minimize this a little so you can see the hint again. So first, I mean, as you can see that definite integration is just one further step from indefinite integration. The main thing is you have to come up with the antiderivative. Then only you can substitute the upper limit and the lower limit. So how to get antiderivative of e raised power minus x? You have to understand it is basically this type of thing. It is e raised power a linear function where the linear function is minus x. The coefficient of x is -1 and the constant term is 0. So it is no different to what we've discussed about. So basically you just use this concept for exponential of a linear term, you use this concept, but only that linear term here is minus x. Okay, so it becomes minus of e raised power minus x plus c. Okay, so let's come to this one. So this will become minus of e raised power minus infinity. That's the upper limit. Minus of minus e raised power 0. That's the, because integration of e raised power minus x is e raised power minus of e raised power minus x plus. So the value at the upper limit is minus of, okay, so this is minus 1 upon e raised power infinity. We can write it like this, minus of minus 1. So it's interestingly 1. Yeah, very good. So all of you got this correct. Aparna, Anirudh, Nidish, Aryan. Okay, so as you can see, once you are familiar with the basic process of indefinite integration, definite integration is just one further step. Okay. Now let's finally, for today's last thing, let's understand area under a curve from definite integration. So this will give us the geometrical interpretation of what we mean by indefinite integration or what we calculate indefinite integration. So if a particular function fx has a graph like this, let's say this is the graph of y is equal to fx, and this is the point x equal to a, and let's say this is the point x equal to b, then the area enclosed or the area subtended by the graph between the points x equal to a and x equal to b, which means basically this shaded area, is nothing but the definite integration. Okay. So the area bounded by the graph, or basically what we mean by the graph is the curve y is equal to fx, okay, and the lines x equal to a, x equal to b, and y equal to 0, or the x-axis. So basically you can see this horizontal line, which is the x-axis, these two vertical lines x equal to a and x equal to b, and this curve y equal to fx. These four boundaries are bounding some area. So this area bounded by all this is calculated by the definite integration of fx from x equal to a to x equal to b. So just as an example, we had just seen that integration of x dx from x equal to 0 to x equal to 2 was 4 by calculation. We had just seen, sorry, it was 2, okay, by calculation. So let's just verify that. So if you see, so this area C is half into base into height is 2. But same way, if we see -1 to 1, this would come out to be 0. Now we can see that this area when we use the algebraic meaning of the term area, this area will become 0. Because this area will be considered as a negative area, and this will be considered as a positive area. So we'll discuss in more detail about this in the next lecture, okay, that how exactly this happens, okay, that it gives us the area under the curve. But I've just shown you with these two examples.
So it's actually that f of x is equal to y, and I'm integrating it, means I am adding all the values of f into x, y into x, right?
No,
So-
it doesn't exactly mean that, beta, because here we are integrating fx dx. No? So you're taking y dx. Y dx is like a very thin strip.
Okay, sir.
Dx is a small interval in x. No?
Yes, sir. And as y keeps changing, I'm
Yeah,
actually
y keeps
all those
changing.
thin strips, right?
Yeah, it is only for a constant function that it is y into delta x. Otherwise, it is a variable value of y which you are integrating with respect to x.
Yes, sir.
Okay, so as I said, we will discuss both the things in more detail next time. More examples of integration by substitution. Today we have seen only the simple type of substitution where we are substituting a linear function with z. So we get that direct formula based kind of integration. But let me also tell you that most of the applications of integration that we see in physics will be covered by what we have done today. Okay. It's only some more situations of integration by substitution which will come at a later stage in physics, in chapters like electrostatics, etc. So some more specific substitutions we'll see. But by and large, for solving problems especially related to mechanics and physics, what we have seen in integration today will give you enough tools. Okay. So we still have work to do in integration, but the basics are done, and from this you can proceed ahead. So now we can also look towards completion of the exercises in the module along with further worksheets. But before I conclude, there are some particular questions from the worksheet last time that I want to still give you some basic hints about, okay, or some basic discussion about, so that maybe you can give them a try today before you go through the answer key and the solutions that I will send. So actually, before going through the solutions, I want you to give these another try, because some of you have requested for some particular questions to be discussed also. So I will keep some time aside in the next lecture for a more formal discussion of these questions also, but I'll just start up by giving you some hints. So for example, in this function, okay, what we can understand for domain and range. So domain obviously will be all real numbers. Okay, because sin x and cos x are defined for all real numbers now. But as far as range is concerned, what we can do is we can understand that y as a function here, it is a periodic function, because cos square x, it ranges between 0 and 1, and sin x ranges between -1 and +1. Okay, so basically what happens is that, and this happens periodically, repeatedly, that means it repeats. This also happens periodically. So anytime we have a periodic graph, it's going to be a graph of this kind of nature. It keeps repeating itself. So the the global maxima will be a local maxima, and the global minima will be a local minima. So that is one way of dealing with this function. Okay. So what you need to do is you need to find the local maxima and local minima by the general method that we discussed, and from that you can calculate the global maxima and minima. And the other question I wanted to give you a hint about, is this one. So we want to find the local maxima and minima for these functions. So let's just go over the steps once more. Same steps you'll apply to all the things. So first step is find the derivative of the function, find the second derivative of the function. So derivative here is differentiation of this. So you can see that that is 2 cos x into minus sin x, okay, plus sin x. So it is sin x into 1 minus 2 cos x. Second derivative is differentiation of this. Okay. So you can use product rule over here, or you can also write this as minus sin 2x plus sin x, and then use chain rule to differentiate this. So either way, when you do that differentiation, you will get minus cos 2x by 2, sorry, minus 2 cos 2x by 2, okay, plus cos x. So that is your first step, finding the derivative and second derivative. Second step is what you have to find the roots of f prime x equal to 0. for that you use this. Okay, so sin x into 1 minus 2 cos x is equal to 0. So this is a very critical step. So sin x can be 0 or cos x can be half. So that means x can be 0, pi, 2 pi, this kind of thing, or x can be here pi by 3, okay, or minus pi by 3. So 2 pi by 3, 2 pi plus pi by 3, or 2 pi minus pi by 3, and this kind of values. Okay. So if you look at the fundamental period of the function between 0 and 2 pi, then these are the critical points you're getting. You're getting 4 critical points: 0, pi, pi by 3, and 2 pi minus pi by 3. So that is 5 pi by 3. Okay. So in a fundamental period, 0 to 2 pi, you'll get 4 critical points. 0, pi by 3, pi, and 5 pi by 3. Okay. So now at each of these critical points, you do the second derivative test. Okay. That is, calculate the value of this quantity at each of them. So for whichever values you're getting negative value of second derivative, you are having a local maxima. And for whichever values you're getting positive, you're getting a local minimum. Okay. So I will send you the solution with the steps and all, but you can just try it out based on this hint now before going through my solutions. Yes, Rijita, you have a doubt, beta?
So sorry, sir, but our school starts from 9:40.
Yeah, I will just finish up. Okay. So just give me 1 more minute. Okay. Just quickly finish up. Yeah, for this one, the hint I'll just give you is that you take this perimeter as 320. Okay. So take this as some variable quantity x. So this quantity becomes L minus 2x. So the area that we are bounding here, this area is x into L minus 2x, or Lx minus 2x square, which is basically 320x minus 2x square. So this is now a function. So what we have to do is you have to calculate the maxima of this function. Okay. So use maxima minima concept to calculate the maxima. So that will give you the maximum possible area that we can. Okay. Because the fence is 3-sided, remember. So the total perimeter of the fence is the sum of the 3 sides. So it is 2x plus L minus 2x. So that's why this side is L minus 2x. Okay, so that's it for today's session, people. Thanks for attending, and sorry for extending and getting into your school time. So we'll conclude here today.
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye.
I wish you a nice day.